In orthogonal curvilinear coordinate system, till now we have discussed several results. You have obtained the expression for arc length, volume element, gradient of a scalar function, divergence of a vector function, curl of a vector function, and particularly the expression for Laplacian operator. Now we will use these results in discussing the special orthogonal curvilinear coordinate system. In fact, our aim is to find these things in particular orthogonal curvilinear coordinate system like Cartesian coordinate system, cylindrical coordinate system, and spherical polar coordinate system. So for your convenience, I have mentioned here all those results which will be needed for this and which you have already studied in the previous lectures. So you can see in orthogonal curvilinear coordinate system, we have obtained the expression for arc length like this: ds square equal to h1 square du1 square plus h2 square du2 square plus h3 square du3 square. And you know these h1, h2 and h3 are known as scale factors. Similarly, we have obtained the expression for volume element like dv equal to h1, h2, h3, du1, du2, du3. And you can see the expression for gradient of a scalar function here, and similarly the expression for divergence of a vector function f like this. You have already seen these expressions, how these expressions can be obtained in orthogonal curvilinear coordinate system in previous lectures. The expression for curl is also mentioned here, and the expression for Laplacian in orthogonal curvilinear coordinate system I have again mentioned here, which we have already studied in the previous lectures. Now particularly we are going to find these quantities in a special curvilinear coordinate system. We will actually discuss three special curvilinear coordinate system which are Cartesian coordinate system, cylindrical coordinate system, and spherical polar coordinate system. Among these, actually the Cartesian coordinate system is most used and most popular, or you can say the most easy to. So first of all, we will see these things in particularly Cartesian coordinate system, and after that we will discuss the same things in cylindrical and spherical polar coordinate system. So you can see just in this lecture I am going to discuss these things in Cartesian coordinate system, which is a orthogonal curvilinear coordinate system. And as you know, in Cartesian coordinate system, the three mutually perpendicular axes are x-axis, y-axis, and z-axis, which I have shown in this figure. You can see, and as in this case the general curvilinear coordinates are denoted by the symbol x, y, z, or x1, x2, x3. So in this case you can say that in this case means in Cartesian coordinate system, actually the coordinate u1 is equal to x. Similarly, u2 is equal to y, and u3 is equal to z in this case. Now you know the expression for the arc length in general orthogonal curvilinear coordinate system, which we have just seen here. You can see this is the expression for arc length ds square, and this has been defined in orthogonal curvilinear coordinate system. Now we will apply this result to the Cartesian coordinate system. So now we know ds square equal to h1 square du1 square plus h2 square du2 square plus h3 square du3 square. But as you can see, u1 is equal to x1. So du1 will be dx1, sorry, not x1 but x. And u2 is equal to y, so du2 will be equal to dy, and du3 is equal to dz. So let us replace du1, du2 and du3 by dx, dy and dz. So in this case you can write this expression as h1 square dx square plus h2 square dy square plus h3 square dz square. Say this is equation 1. But in Cartesian coordinate system, you know what is the expression for ds square. So, but in Cartesian coordinates, this ds square is equal to simply dx square plus dy square plus dz square. As you know, x, y and z are independent variables. So dx, dy and dz will be also independent from one another. In this condition, if you will compare equation 1 and 2, then you will find that if these two equations are equal, then definitely the coefficients of dx square, dy square and dz square in equation 1 and 2 must be same. And therefore, you can say h1 square will be equal to 1, h2 square will be also 1 and h3 square will be also 1. It means h1, h2 and h3, all these three scale factors will be 1 in Cartesian coordinate system. This is a very remarkable result. So therefore you can say, comparing equation 1 and 2, we will find that h1 is equal to h2 and this is equal to h3 and all these three will be equal to 1. Now in Cartesian coordinate system, the unit vector e1 hat is generally denoted by I hat. The unit vector e2 hat is denoted by j hat in general, and e3 hat is denoted by the symbol k hat. So we will also replace e1, e2 and e3 by ijk. Now one by one you can find what will be the expression for different quantities in Cartesian coordinate system. So now let us start to get the expression for different quantities which we have discussed in general orthogonal curvilinear coordinate system in previous lecture. So first of all, we will see what will be the volume element. Volume element. You have seen just now that the volume element dV in orthogonal curvilinear coordinate system is given as h1 times h2 times h3 du1 du2 du3. But as in case of Cartesian coordinate system, you have seen all these scale factors are 1. So this will be simply 1 times 1 times 1, and du1 is dx, du2 is dy and du3 is dz. Therefore, the volume element in Cartesian coordinate system is simply given as dx into dy into dz. This is the simplest expression for the volume element, but vividly used. Its use is in fact very greater in comparison to other coordinate system. Now we will find the expression for gradient of a scalar function in Cartesian coordinate system. So let us see what will be the expression for gradient of a scalar function in Cartesian coordinate system. As you know, in general curvilinear coordinate system, grad phi, where phi is actually a scalar point function, and equivalently it is written as del phi. You know the expression for this is what? This is 1 over h1 del phi by del u1 e1 hat plus 1 over h2 del phi by del u2 e2 hat and plus 1 over h3 del phi by del u3 e3 hat. You can see I have mentioned this result earlier. You can see it here. Now if you want to apply this result for the Cartesian coordinate system, then you have to see what are the values of h1, h2 and h3 and how we denote the unit vectors e1 hat, e2 hat and e3 hat. So you know, you have seen that these scale factors h1, h2, h3 are actually equal to 1. e1 hat, e2 hat, e3 hat are denoted by ijk and u1, u2, u3 are denoted by xyz. So you can see since this h1 is 1, so this will be simply del phi by del x I. We have written here x instead of u1 and I instead of e1 hat. Similarly, since h2 is also 0, so this will be del phi by del y j hat and plus the last term will be del phi by del z k hat. This is actually the expression for gradient of a scalar function phi in Cartesian coordinate system. Now you can define in similar manner what will be the divergence of a vector function in Cartesian coordinate system. See here. As you know, you have seen the expression for divergence of a divergence of a vector function f in orthogonal curvilinear coordinate system, and the expression you can see here. I am just repeating this expression for your convenience. You can see it here that this expression is divergence of f, which is equivalently written as del dot f. And how it is defined, you have seen this is defined as 1 over h1, h2, h3 del u1 f1 h2 h3 plus del u2 f2 h1 h3 and plus del u3 f3 h1 h2. You can see this is your definition of divergence of f in orthogonal curvilinear coordinate system. So I have mentioned it again. Now we will apply this expression in Cartesian coordinate system. But you know, in Cartesian coordinate system, all these scale factors are 1. So the product h1, h2, h3 will be equal to 1. u1, u2, u3 will be again replaced by x, y, z. And in this case, you can write that this del dot f, या divergence of f, this will be simply equal to del f1 by del x plus del f2 by del y plus del f3 by del z. People also write fx, fy, fz instead of f1, f2, f3. So you can replace f1, f2, f3 by fx, fy, fz, where actually fx, fy, fz are the orthogonal components of the vector field f in x, y, and z directions. So you may write equivalently like this. This is del fx by del x plus del fy by del y plus del fz by del z. So this is actually the expression for divergence of a vector field f in Cartesian coordinate system. Now we will find the expression for curl of a vector function in Cartesian coordinate system. So how we will define it, you can see it here for curl. You have seen earlier how curl of a vector function f is defined in orthogonal curvilinear coordinates. You have seen this is expressed in the form of a determinant. This is 1 over h1, h2, h3. You can see the definition here. This is your definition of curl of f, and this is defined like this: 1 over h1, h2, h3, and this determinant. I am just repeating this result for your convenience here. You can see this is determinant of h1 e1 hat, h2 e2 hat, h3 e3 hat, del del u1, del del u2, del del u3, and here there will be h1 f1, h2 f2, h3 f3. This is actually the definition of curl of a vector field f in orthogonal curvilinear coordinate system. And you can again see, if we apply this result to the Cartesian coordinate system, we will simply take h1, h2, h3 equal to 1. e1 hat, e2 hat, e3 hat will be replaced by ijk, and u1, u2, u3 will be replaced by x, y, z. So after replacing these, you can see what will be your expression. Making these substitutions, you can see that curl of f in Cartesian coordinate system will be simply equal to the determinant I j k del del x del del y del del z. You may also replace f1, f2, f3 by fx, fy, fz. So I am writing here fx instead of f1, fy instead of f2, and fz instead of f3. So this is the expression for curl of f in Cartesian coordinate system. And I hope you have an idea of these things already, because you have studied it in the differential part of vector calculus. Now finally, we are going to find the expression of Laplacian operator in Cartesian coordinate system. So what will be the expression for Laplacian? You can see it here. Laplacian, which is denoted by this symbol del square. And as you know, the general expression for the Laplacian in orthogonal curvilinear coordinates is like this. You can see it here. I will repeat this expression for your convenience again. So first see this expression, how this del square is defined. You can see. So I am just repeating the same result. This is in fact 1 over h1, h2, h3, as you can see it here. This is 1 over h1, h2, h3. And del u1, h2, h3 over h1 del u1 plus del u2 h1 h3 over h2 del u2 and plus del u3 h1 h2 over h3 del u3. This is the expression for Laplacian in orthogonal curvilinear coordinate system. But here again you can see these scale factors are 1, and we will replace u1, u2, u3 by xyz. So after making this substitution, you will get that the expression for del square in Cartesian coordinate is very simple. This will be del 2 by del x square. In fact, this del u1 will be operated on del u1, that will be del square del u1 square. So this will be del square del x square plus del square del y square plus del square del z square. This is the expression for Laplacian in Cartesian coordinate system. Actually, the expression for these things in cylindrical and spherical polar coordinate we will discuss in the forthcoming lecture. And actually, these expressions are very important and always used in almost all branches of physics. So these expressions are very important. You should remember it. And if you remember the expression for these things in orthogonal curvilinear coordinate system, and you know you have an idea of the scale factors in a particular coordinate system, then in that particular coordinate system you can easily write what will be the expression for these things in particular or a special curvilinear coordinate system like Cartesian, cylindrical and spherical. So in this lecture I would like to finish my lecture here, but in forthcoming lecture as I have told you, we will discuss in particular manner the cylindrical coordinate system and the spherical polar coordinate system.